The goal of this series of videos is to help you understand the basic scientific concepts that underlie the way that Earth's climate system works. If you are a serious and humble student of Earth science, and if you are truly interested in improving your understanding of the science of Earth's climate system, these videos might be very helpful to you. In the first video, I introduced the concept of Earth's radiation budget. My goal in this second video is to help you be familiar with the actual wavelength ranges of the radiation given off by the Sun and the Earth. This will be important background for many areas of Earth science and climate science. For example, the interaction of incoming solar radiation with certain components of Earth's upper atmosphere, mainly in the stratosphere, leads to the presence and activity of the ozone layer. And as we'll see in the part 3 video, the interaction of outgoing terrestrial radiation with certain components of Earth's atmosphere, mainly in the troposphere, leads to the greenhouse effect. The radiation which is given off by the Sun, which is of course called solar radiation, and the radiation given off by the Earth, which is called terrestrial radiation, are both described nicely by well-established physical theories of blackbody radiation. As is described by blackbody radiation theory, any physical object that has a non-zero temperature in the Kelvin scale gives off radiation. This is a mechanism by which objects in space come into thermal equilibrium even if they're not directly touching. I'm going to use a simulator which is available for free online to explore the general features of blackbody radiation. This simulator has been provided by the good people in the physics department at Colorado University. We'll use it to look specifically at the radiation given off by the Sun and the Earth. And we'll see that the radiation, in terms of the amount of it and the wavelength range given off by these objects, it's all controlled by their temperatures. So let's go to that site. Let's use this simulator to first consider an object that has the same temperature as the surface of the Sun. We can control the temperature of a virtual object with this vertical slider bar. So let's go from this starting temperature that it defaults to and increase it to the surface of the Sun. So basically the Sun gives off a range of frequencies. So this red curve on the simulator is a curve of emission intensity as a function of wave. It's quite a broad curve. This curve, however, has a maximum to it, which tells us the wavelength of maximum emission. So specifically here for the Sun, the wavelength maximum emission falls in the visible range, just shorter than 500 nanometers. As a side note, you might understand the basic intelligence of green photosynthetic plants. They have evolved to take advantage of photons in the visible wavelength range, i.e. those incoming energy-carrying photons that have the greatest abundance at Earth's surface. Concepts of evolution aside, now that we've modeled the radiation emitted by the Sun, let's look at the radiation given off by the surface of the Earth. The Earth, of course, is an object that has a much lower temperature. So let's first generally look at what happens to the blackbody radiation as the temperature of our virtual object changes. We'll take the slider bar and just lower it down a little bit. You can see two things happening as we decrease the temperature of the object. The first is that the curve broadens. It becomes harder and harder to discern the wavelength of maximum emission. The second is that the wavelength of maximum emission shifts and moves towards longer wavelengths. Another point that I should make is that the total amount of energy given off by the glowing object is proportional to the area under the curve. So you will see that the total amount of energy given off by a lower temperature object decreases. Now let's decrease the temperature all the way down to the temperature of the Earth. And these people who built these simulators quite often, I think, had Earth science in mind. The temperature of the Earth is actually one of the reference points on this axis. So we'll just go down to that. You see, there's two things we have to do to locate that maximum. Zoom in on the vertical axis, basically move out a little bit on the horizontal axis. There it is. After making appropriate changes to the vertical and horizontal axes of the graph, we can see that the wavelength of maximum emission by the Earth lies about 10,000 nanometers. It's a broader curve, and the maximum is not as sharp or clearly defined, but the maximum of emission is around 10,000 nanometers. Correspondingly, those are much lower energy photons. But nonetheless, the Earth is glowing, it's radiating off photons. Now, we'll transition to my next slide, which shows these two curves plotted side by side, or in overlay fashion. I think plotting the emission spectra of the Sun and the Earth together like this lets you see that really these phenomena are fundamentally the same. They are just objects that are glowing because they have some temperature. But of course, the two curves are very different in terms of the total area under the curves and the wavelengths of maximum emission, because they have two very different temperatures. But nonetheless, on a certain physical level, there's a fundamental similarity in the phenomena that both glow. However, okay, so this wavelength range difference in the emission given off by the Sun and the Earth is a nice little bit of detail to understand. Again, if you want to understand the effects that the incoming radiation has on Earth's atmosphere, such as creating the ozone layer and some of it being absorbed by the ozone layer, and then if you want to understand the effects of the outgoing radiation, and as we'll see, we're going to talk about the wavelength ranges of those outgoing photons being important as we try to understand the greenhouse effect, etc. It's really good to have this background knowledge that the radiation falls in very different wavelength ranges. Okay, see you with the next video. Thanks for watching.